Welcome back, students. In the last exercise set, we explored interfaces in action. You learned how to design contracts for behavior and implement them across diverse classes. Now we're going deeper. This session includes more hands-on exercises that focus on polymorphism, interface design, and real-world modeling. You'll see how the same method, like recover or turn, can express completely different behaviors depending on the class. Let's jump in. Let's begin with our first exercise called recovering. The idea is simple but powerful. We have multiple objects, patient, upholsterer, and football player, that all need to perform a recovery action. We'll define a common interface called iRecoverable with a method recover, and each class will implement this method in its own way. This is a great use case for polymorphism, one interface, many behaviors. Each class should implement this interface and define recover in a way that makes sense in its context. This teaches students how to use a common contract for varied behaviors. Here we define the iRecoverable interface. It's simple. It contains one method, recover, but this single method acts as a contract. Any class that implements it is obligated to provide its own behavior. This is crucial in large systems. We program to an interface, not an implementation. It gives us abstraction and flexibility. The patient class implements this interface. Its version of recover prints, I am getting better. This models recovery in a health context. The key takeaway, interfaces allow us to write code that's independent of specific class names while preserving behavior. Next, the upholsterer class implements iRecoverable. Its implementation of recover says, I have new material for the couch. This reinforces that the method name stays the same, but its meaning adapts to the context. This is what semantic polymorphism is all about. Finally, the football player class also implements iRecoverable. When we call recover on a football player, the message is, I picked up the ball after a fumble. Again, same interface, but here recovery has a sport-specific meaning. This makes our system open for extension. We can add more recovering types later without changing existing logic. In the main method, we declare three objects using the interface type. We assign a patient, upholsterer, and football player to iRecoverable references. When we call recover, the correct method is called for each one. This is dynamic dispatch. This is how C# uses polymorphism with interfaces to resolve behavior at runtime. Now we store our different objects in a single list of type list iRecoverable. This is powerful. We can treat all these diverse objects uniformly through their shared interface. The for-each loop iterates and calls recover on each one. The runtime dynamically resolves the correct implementation. This technique is essential when working with heterogeneous collections in enterprise applications. Here we define a method help recover that accepts any object implementing iRecoverable. This is decoupling in practice. The method doesn't care what the specific type is, only that it knows how to recover. This improves reusability and reduces dependency on concrete classes. Notice also the distinction between direct and interface references. Direct references expose all class members, while interface references restrict access to interface-defined behavior. This method prints the name of the object and calls its recover method. The benefit is clear. We can create general-purpose methods that can operate on any type that satisfies the interface. This reduces code duplication and increases flexibility. Again, this showcases late binding. Behavior is resolved at runtime based on the object type. This recaps why we use interfaces. They allow polymorphism, flexibility, and abstraction. Interfaces enable us to design by behavior, not by structure. They are especially useful when working with collections, delegating behavior, or designing frameworks that expect certain capabilities from unknown types. This function demonstrates using interface polymorphism in method calls. Any object implementing iRecoverable can be passed in. This makes your methods highly reusable and testable. You're not locked to specific types, you're programming to an abstraction. Here, the classic example is implemented. We create the three class instances and call their recover methods individually. This is a straightforward approach, but it lacks the generality of the interface-based solution. It's a good comparison point to show the added power interfaces bring. We've now demonstrated the power of interfaces as contracts, how polymorphism works in collections and method arguments. The difference between interface-based design and class-coupled code. All of this prepares you for writing clean, reusable, and testable code. We now move to a new interface, iTurnable. It defines a contract for objects that can be turned. Each class, page, corner, pancake, and leaf, implements turn in a way that fits its meaning. This allows us to reuse the same interface structure across very different objects while customizing behavior. These are the individual implementations of the turn method. Each class captures its domain's logic. The page is turned in a book, the corner in a road, and so on. This again shows polymorphism, different actions bound to the same interface method signature. Each class, page, corner, pancake, implements the turn method differently. This reinforces the idea that the interface defines the what, and each class defines the how. We complete the implementation with Leaf. Finally, in the turning demo class, we create instances of all classes and call turn on each. This shows once again how interface-based programming makes your code clean, modular, and flexible. Here's the execution. The turn method is called on each class instance. It's the same method name, but the action varies. This reinforces the separation of interface, what, from implementation, how. Your code becomes simpler and more intuitive as behaviors are neatly compartmentalized. Through these exercises, we've seen interfaces not just as syntactic structures, but as powerful tools to design scalable, modular, and maintainable systems. They allow us to enforce behavior contracts, simplify polymorphic behavior, and generalize code that can work with many types. Understanding interfaces lays the groundwork for more advanced design patterns and principles you'll encounter in real-world development.